Today we will be going through Physical Sciences June 2023 Paper 1 exam, starting from question 6. Diving right in. We are told that a car moves at a constant velocity of 22 meters per second on a straight horizontal road towards a stationary device, which can both emit and detect sound waves. The device emits sound waves with a frequency of 240 Hz. These sound waves are reflected off the car, and the reflected sound waves are then detected by the device, as shown in the diagram below. 6.1.1 State the Doppler effect in words. You have two key phrases, the first being change in frequency, and the second being the source and the listener have different velocities relative to the medium of propagation. Now, how you would tie it in together, you would then say the Doppler effect states that the apparent change in frequency of the sound detected by a listener, because the source and the listener have different velocities relative to the medium of propagation. So the Doppler effect is the phenomenon whereby the apparent change in frequency detected by the listener is because the source and the listener have different velocities relative to the medium of propagation. Or you could say it is the apparent change in observed or detected frequency as a result of the relative motion between a source and an observer. Question 6.1.2 being a calculation. 6.1.2, we are told that, if the speed of sound in air is 340 meters per second, calculate the frequency of the reflected sound waves detected by the device. Okay. Now, in this scenario, you would then start with your formula, which tells you that the frequency of the listener is equal to the velocity of sound plus minus the velocity of the listener over the velocity of sound plus minus the velocity of the source times the frequency of the source. Now, we know that the speed of sound we have been given as 340. And now, as we look at the diagram, the car is moving at a constant velocity towards the stationary device, meaning at this point we are going to add the velocity of the listener. Okay, so that's going to be plus 22 divided by 340 plus or minus the velocity of the source is 0, because the device that is emitting the sound is stationary, therefore its velocity is 0. And we are told that the frequency emitted by the source, which is this device right here, is equal to 24,000 Hertz. And then your final answer tells you that the frequency observed by the listener is equals to 25,552.94 Hertz. Wonderful. Then 6.2. The spectral lines observed for a distant star show that the star is moving away from Earth. Explain by referring to frequency how one can deduce that the star is moving away from the Earth. So if the star is moving away from the Earth, it means that the spectral lines that we observe coming from the certain star are going to be redshifted, meaning it's going to be going towards the lower end of the electromagnetic spectrum, the lower end of the frequency spectrum. Okay, so that means if a star is redshifted, it means that the frequency is decreasing. Remember that for redshift, you find, say maybe these are your okay, let's draw our spectrometer, and you are looking at your blue side, which turns more purple and finally becomes red. So the further you move towards the red side, the greater the wavelength. It means that remember that on the electromagnetic spectrum, right, on the visible light spectrum, the color red has the longest wavelength. Thus, it tells you that wavelength increases as you go higher, and as wavelength increases, it tells you that frequency also decreases. Therefore, to answer this question, you would then say, since the spectral lines show that the star is moving away, the frequency will be lower due to the redshift. Okay, so explain by referring to frequency how can one deduce that the star is moving away from Earth. You can just say that the frequency of the spectral lines would decrease, okay, with your keywords being frequency and decrease. Without those two keywords, you would not get full marks. So that is it for our Doppler effect question. We may then go on to the Coulomb's law question, question 7. Now, question 7 tells us that 2-point charges X and Y are held 0.03 meters apart. As shown in the diagram below, the charge of X is minus 7.2 times 10 to the minus 9 coulombs, or minus 7.2 nanocoulombs, if you will, while the charge of Y is plus 7.2 nanocoulombs. The first question asks us to state Coulomb's law in words. Now, for this one, you need multiple keywords. Okay, so I'm just gonna write out the entire law. You will have that the magnitude of the electrostatic force exerted by a point charge on another point charge is directly proportional to the magnitude of the charges and inversely proportional to the square of the distance between them, with your keywords then being electrostatic force and directly proportional to there should be a to the product of the magnitudes of the charges. Okay, so your keywords will be electrostatic force directly proportional to the product of the magnitudes of the charges, and finally inversely proportional to the square of the distance between them. Those are your keywords. Moving on to 7.2. Draw the net electric field pattern due to the 2-point charges. Now we know that our electric field lines flow from positive to negative. Thus, this will be our X, that will be our Y, and that will be our electric field lines. Do not mind my drawing. As I have said multiple times, my drawings are quite horrible. Thus, you will then have this kind of shape, okay? You will get marks for correct shape. You will get marks for the correct direction from Y to X. And finally, the lines must not cross each other. And for that, you will get a cross. You will get a mark for that. Let's go to 7.3. Well, 7.3 is asking us to calculate the magnitude of the electrostatic force that Y exerts on X. Now, we know Coulomb's law tells us that the electrostatic force exerted by one point particle on another point particle is equal to is directly proportional to the product of the magnitudes of their charges and inversely proportional to the square of their distance, okay, with some proportionality constant K. Okay, from here, we know our Coulomb constant is 9 times 10 to the power 9. We know one charge is 7.2 times 10 to the power minus 9. The other charge is also 7.2 times 10 to the minus 9. All divided by the distance between them given in the problem statement, 0.03 meters squared. Thus, the force exerted by Y on X is thus 5.18 times 10 to the minus 4 newtons. Great. Now, the next question asks us to draw a labeled diagram to show the directions of the electric fields at the point where X is positioned. Okay, 7.4. Draw a labeled vector diagram to show the directions of the electric fields where at the point where X is positioned. Okay. Oh, we have another problem statement. A third point charge Z of unknown positive charge is positioned at 0.01 meters to the left of the point charge X on the line joining point charges X and Y and shown in the diagram below. So for 7.4, seeing as this is a positive charge, This is a negative charge and this is a positive charge. Clearly, our electric field line will be flowing from positive to negative from either side. Thus, if we are to draw a vector diagram, we would then say EY is going that way. This is the position X, and EZ is going that way, the electric field provided by Z. Or you could choose to draw it in a way where EZ is still going that way. That is your point charge, and EY is also going that way. Or you could also draw it in a way where EZ is that way and EY is that way. Each one of these options is equally viable. And finally, 7.5. The magnitude of the resultant electric field at the point where X is positioned is 4.91 times 10 to the power 5 newtons per coulomb. Okay. Calculate the magnitude of the charge on Z. Now, we are told that the magnitude of the resultant force that is felt by X is 4.91 times 10 to the power 5 newtons per coulomb. Okay. Now, we know our electrostatics laws tell us that the net electric field is given by EZ plus EY at the point where X is, right? But since these two are pointing in different directions, we may thus write EZ minus EY. Because remember, from our vector diagram, they are pointing in different directions. So if we take the right to be positive, then that tells you that EZ is the positive component and EY is the negative component. And also Coulomb's law tells us that the electric field is equal to KQ over R squared. Therefore, E net is equal to K all into QZ over R squared minus QY over R squared. Okay, that's gonna be 9 times 10 to the power 9, which is our Coulomb constant, multiplied by QZ, because we don't know what QZ is. That is what we are trying to find. The given distance between X and Z is thus 0.01 squared minus QY is given as 7.2 times 10 to the minus 9. And the distance is 0.03 squared. The net electric field is given as 4.91 times 10 to the power 5. Then after all of our algebra, where you have QZ being equal 9 times, sorry about that, being equals 4.91 times 10 that's 4.91 times 10 to the power 5 divided by 9 times 10 to the power 9 plus 7.2 times 10 to the minus 9 over 0.03 squared, all multiplied by 0.01 squared. This then tells you that QZ is equal to 6.25 times 10 to the minus 9 coulombs. Wonderful. You could use a different approach to the question where you use force considerations. Okay. Option 2. So for force considerations, what you would do is you would start with stating that the electric field is given by the force over the charge. Because remember that the electric field, the dimensions of the electric field, or the SI unit of the electric field, are newtons per coulomb. Okay, so this is force per unit charge. So E is equal to the force divided by the charge. Now we are told that the electric field is 4.91 times 10 to the power 5, which is equal to the force over 7.2 times 10 to the minus 9. Thus the force is given by 3.54 times 10 to the minus 3 newtons. Okay. From here, because the forces are additives, because remember that these forces are acting on the same plane, that therefore because they are acting along the same axis, they're acting on the same plane along the same axis, they may then be additive. Okay, so that means that the net force is given by Fz on x plus Fy on x, okay, which is equal to K Qz Qx over r squared plus K Qy Qx over r squared. Okay. Then from here we know that the net force is 3.54 times 10 to the minus 3, which is equal to 9.0 times 10 to the power 9 into 7.2 times 10 to the minus 9 multiplied by Qz, all over 0.01 squared, minus, we've already calculated the electrostatic force that is exerted by point charge F on point charge Y, which is way up here. We found it to be 5.18 times 10 to the minus 4 newtons. Okay, so we just plug that in there to give us 5.18 times 10 to the minus 4. Working out the algebra then gives you Qz is equal to 6.26 times 10 to the minus 9 coulomb. Now, both of these are correct because we use different methods. You need to keep in mind that sometimes the answer in physics isn't exact because there's multiple ways in which you could approach a question, and the different ways that you could approach with the question have different errors associated with such questions. So don't really get scared or get worried when you see such things happening, as long as the answers are close enough together, or they fall within a certain range, then you are pretty much safe. So good, we are done with question 7, as we have finally calculated the net charge, the charge on Z. And now we'll be moving on to question 8. I'll just remove this here to make our lives easier. Now, question 8. 8.1, state Ohm's law in words. Okay, now Ohm's law states that the potential difference across a conductor is directly proportional to the current in the conductor at constant, okay, no, that's too much, constant temperature. That's it. So your keywords being potential difference and directly proportional to the current, and finally at constant temperature. So you could just write the potential difference is directly proportional to the current at constant temperature, and you will be fine. Or you could say the ratio of potential difference to current is constant at constant temperature. Or you could say the current in a conductor is directly proportional to the potential difference across the conductor at constant temperature. Now, 8.2. Here we need to calculate, so we will be reading the problem statement. Okay. A battery with unknown EMF is given, a battery of unknown EMF and unknown internal resistance is connected to 3 resistors, a high resistance voltmeter, 2 switches, and 2 ammeters of negligible resistance, as shown below. Both switches S1 and S2 are closed. The reading on ammeter A1 is 1.5 amperes. Calculate the reading on the voltmeter. Now, the reading on the voltmeter is going to be equal to, obviously we're going to be, not obviously, but we will be using Ohm's law. And Ohm's law tells you that the ratio of the potential difference across a conductor, it tells you that the potential difference across a conductor is directly proportional to the current in the conductor at constant temperature. We know that V is equal to IR, okay? Now, the resistance R is going to be the resistance that is flowing through this entire circuit when it comes there, okay? So the resistance is going to be the resistance that is flowing through the entire circuit, which is this resistance, okay? Now we're going to take that resistance and then what are we going to do with it? We are going to plug it into the formula. Thus, V is equal to, the current is given as 1.5 into 7, and that is 10.5 V. Or a different way you could use this is you could use just one of these resistors. Okay, you could use just one of these resistors to have you could use either one of these resistors to calculate the potential difference across each resistor, okay? Because this is connected in series to both these resistances, okay? So if we then take the potential difference across each resistor and then add up the potential difference that is found for each resistor, we can then find the total potential difference. So working through that using our formula of V is equal to IR, we may thus write V is equal to 1.5 into 2, which is equals to 3. And we can write V is equal to 1.5 into 5, which is equal to 7.5 V. Therefore, V total is equal to 3V plus 7.5 V, which is just 10.5 V. Or volts. Yeah, it's better if I actually say volts to avoid confusion. Now, we may thus move on to 8.2.2. We are required to calculate the reading on ammeter A2. Okay. Now, using our formula, we may write our formula for Ohm's law, of course. We may write that V is equal to IR. Now, because V is equal to IR, now what are we going to use? Which current? We don't know the current. We don't know which potential difference to use, and we don't know which resistance to use. Okay, but here the trick is resistor A2, okay, is connected in series with, ammeter A2 is connected in series with resistor 3, okay? It's connected in series with resistor 3. And we already know that the potential difference that is moving across this voltmeter is 10.5, okay? So those are the two values that we're going to use. You may be asking yourself, why are we using these values, and why are we not using the values of what we found before? Now, you need to realize that before, okay, we know that for a never mind. We use those two for those reasons, because this ammeter is connected in parallel to this resistor, and the potential difference across this resistor is the same potential difference that is recorded on this voltmeter right there. Okay, so those are the values that we will be using. Thus, we know that our voltage is 10.5. Our current, we don't know, should be I2. Yes, because we are looking for the reading on A2, so I2 multiplied by 3. Thus, the current across resistor 2 is equal to 3.5 A. Now, remember that a series connection is a current divider. Okay, a series connection is a current divider. So because it is a current divider, we must then add up the currents of what we find here, because remember, this ammeter and this ammeter are connected in series, okay? And a series circuit is a current divider. Thus, that means we are going to be adding up whatever is felt here, okay, will be the current that is coming through here and whatever the current is felt there, okay? Therefore, current through A2 is given by I2 plus I1, and that is 3.5 plus 1.5, and that is finally 5 amperes. Okay, or a different way you could use it, a second option would be to use the the resistance, okay, you may find that 1 over the resistance of a parallel connection is equal to 1 over R1 plus 1 over R2, 1 over the resistance of a parallel circuit is equals to 1 over 7, because the resistance that is going through this connection is 7 and the resistance that is going through this section is 3 amperes, okay, and these two sections, okay, these two sections are connected in parallel, okay. So because of that, we may use this relation 1 over 3 such that RP, or the resistance through the parallel connection, is 2.1 ohms. Finally, we know that R is equal to V over I, which is I total, or the resistance that is going through this entire connection, okay, the resistance that is going through this entire connection is what is going to be recorded by this ammeter, okay. So this entire connection is going to be recorded by this ammeter. So that's why we have this I total, okay, that's why we have this I total, because we had to take the total resistance of this entire parallel connection. So finally, substituting in our values, we know that we found 2.1 ohms for the resistance. We know that the voltage through that entire parallel connection is 10.5 volts. And finally, we don't know what the current is, thus the current is equal to 5 amperes. Okay, wonderful. We may then move on to the next question, 8.2.3, the power dissipated in the 3 ohm resistor. Okay. Okay, I'll just do this because we've already been through these questions, so I'll just delete this here. And fine. 8.2.3, the power dissipated in the 3 ohm resistor, okay? Now, the relationship between potential difference voltage and potential difference power and the resistance is given by P is equal to V squared over R, okay? So we know that the V that we got, because we are looking for the power dissipated in the 3 ohm resistor, and the 3 ohm resistor feels a potential difference of 10 ohms, because remember, here is our voltmeter that is measuring that, okay? So that's going to be 10 squared, 10.5 squared divided by 3, and that is 36.75 watts. Option 2, you could use the square current law, where P is equal to I squared R. Remember what I told you about a series circuit being a current divider, meaning this ammeter is going to be recording the current that is flowing through this connection and the current that is flowing through that connection right there, okay? So that tells you that because we are looking at the potential difference measured here, we may thus use the current that is measured here. And for the current measured there, we found that the current is 3.5 squared multiplied by the resistance, and our resistance is just 3. And this gives you 36.75. And finally, your option 3, you have power is equal to the product of the potential difference with the current. And we know our potential difference is 10.5 and our current is 3.5. That gives us 36.75 watts. Please always remember to input your units. I noticed that in some of my calculations I may have forgotten to input my units, so please don't make that mistake. You will lose marks. Yeah, that's 8.2.3. Moving on to 8.4. So I'm doing this just so that we could continuously have view of the diagram. I want us to continuously have a view of the diagram. Now 8.3. We are told that switch S1 is now opened. Okay, switch S1 is now opened. This is switch S1. Okay, I should probably do a better job of highlighting that. Switch S1 is opened. Now, since switch S1 is opened and switch S2 remains closed, the reading on ammeter A2 now changes to 3.64. Calculate the EMF of the circuit of the battery. Okay, now remember that we had to calculate the value of the resistance of the parallel connection, because remember this EMF is let me just choose a different color, but this EMF is supplying a potential difference to this entire parallel connection. Okay, so we're going to need to use the what do you call it, the resistance of the parallel connection. But we already know that the resistance of the parallel connection is equal to 2.1 ohms. We've already calculated that in one of the options that I gave you before. Okay, so then from there we know that if S1 is opened, if both of them are closed, okay, if both of them are closed, we know that since, okay, let's say both closed, because we're going to need to use a simultaneous equation here. Both closed, if both switches S1 and S2 are closed, the EMF is given by I over R plus R, which is essentially just IR plus IR, and this is the internal potential difference plus the external potential difference. Okay, and that is just equal to 5 into 2.1 plus R. Okay, and this comes, let's name this equation 1. Okay, and this 5 plus 2.1i comes from the fact that we used, it comes from here. Remember that the total current felt by our circuit is 5 ohms. Okay, and the total resistance through the parallel connection is 2.1 ohms. Sorry, that's 5 amperes and 2.1 ohms. So now, if switch 2 is open, okay, we have that still the EMF is equal to IR plus R. And if switch 2 is open, okay, let's look at what happens when switch 2 is open. Okay, If switch 2 is open, it disrupts the entire flowing of the circuit. It disrupts the flow of the circuit in this area. Okay, it disrupts the flow of the circuit in that area. However, why would we be keeping switch 2 open? Because then the rest of our circuit will just be moving off that way. Why would we open it? Okay, but now let's consider is if S1 is closed. Okay, if S1 is closed, the majority of our if S1 is closed, right, the circuit is just restricted to this path right here. Okay, this path, because there's nowhere for it to go. If it comes this way, then it's closed. Okay, or it's the switch is open. So it's, if S1 is closed, okay, sorry, if S1 is now open, okay, if S1 is now open, okay, so if S1 is open, we find that the current is 3.64 and the resistance is 3 plus R, okay, and we name this equation 2. Now we come and equate equation 1 to equation 2, because the M for the entire circuit and the smaller circuit are the same. Okay, so now since 1 is equal to 2, we have that 5 into 2.1 plus R is equal to 3.64 into 3 plus R. Okay, our algebra tells us then that R is equal to 0.31 ohms. And then we could take this R and substitute it either into equation 2 or equation 1. Let's substitute into equation 1. This tells us that the EMF is equal to 5 into 2.1 plus 0.31. Thus, this is equal to, the EMF is equal to 12.05 volts. It's also acceptable to write 12.04. Okay, that is the end of that. Moving forward, let's see, 8.4. Now, switch S2. S2 is opened. This one is opened while S1 is closed. Okay. How does the voltmeter reading change? Choose from increases, decreases, or remains the same. Okay. Now, if switch S2 is opened, the resistance of the entire circuit increases. Because now, why does the resistance of the entire circuit increase? Is because if switch S2 is opened, then it cuts off the connection of the 3 ohm resistor to the rest of the circuit, thus making the circuit a completely series connection. Okay, so then that means if the total resistance of the circuit increases, if the total resistance of the circuit increases, then the potential difference then decreases. Okay, if the total resistance of the circuit increases, then the potential difference decreases, because Ohm's law tells us V is equal to IR, or okay, V is equal to that. Therefore, V is directly proportional to R, okay? And if V is directly proportional to R, when R increases, V also increases. Therefore, your answer for 8.4 will be increases. Why? Total resistance of the circuit increases. And we are done with question 8. Question 9. Let's go. All right. Now, we are told that the simplified sketch below represents an AC generator with the coil initially horizontal between the poles of the magnet. X and Y are 2 poles on the coil, while A is one of the poles on the magnet. When the coil of the generator rotates clockwise between the 2 poles of the magnet, when the coil of the generator rotates clockwise between the 2 poles of the magnet, the direction of the induced current is from X to Y as shown above. Okay? Is from X to Y as shown above. Now, is A the north pole or the south pole of the magnet? Okay, that should be easy enough. That is the north pole. 9.2, 9.1.2. Sorry, that's 9.1.1, 9.1.2. Now, this can be determined using the right-hand rule. I don't really know how to demonstrate it to you without having a video, but it's essentially just, you can find it in the textbook or on an internet search. Just go on YouTube and look for the right-hand rule, and you'll be sure to find it. Next, we are told that the coil is now rotated through 180 degrees, okay? Will the direction of the current be from X to Y or from Y to X? Now, remember that in the original configuration of the magnet, the current was flowing from X to Y. Now, the coil is rotated through 180 degrees, which means the direction of the coil is now completely flipped over, okay? So if it's completely flipped over, it means now then that the current is going to change direction also, okay? Or the orientation of the coil changes. So since the orientation of the coil is now the opposite direction, it means that the current will also flow in the direction opposite to what it was flowing initially. So this will be Y to X. 9.1.3. Sketch an M time graph for 2 complete rotations of the coil, starting from the position of the coil as shown in the diagram below. Now, when you look at the coil, okay, when you look at the coil is almost, it's orientated almost perpendicular to the magnets, okay? It's almost perpendicular to the magnets, so meaning that it is parallel to the magnetic field between the two poles of the magnet. Because remember, we said that this is the north pole, right? And our magnetic field is oriented in that direction, okay? So this coil is almost parallel to the magnetic field, so meaning that the M can't be 0. The M can't be 0, so meaning your graph has to start from any point above the 0 point, and it will fluctuate for 1 complete rotation. And that is your M versus time graph. 9.2. 9.2 tells you that an electrical device is connected to an AC generator. The RMS potential difference across the device is 200 volts, and the maximum current passing through the device is 6 amperes. We are asked to calculate the resistance of the device. Now, since we are told that the RMS potential difference across the device is 200 volts and the maximum current passing through the device is 6 amperes, we may use the VRMS formula, which tells you that VRMS is equals to the max voltage divided by the square root of 2. Okay, our VRMS, we are told, is 200 volts. We don't know Vmax, and divide by our root 2. This tells you that Vmax is equal to 200 multiplied by the square root of 2, which is 282.84 volts. Now, moving from here, you may then use Ohm's law and plug in your voltage, where your resistance is equal to the potential difference divided by the current. Now, because we have the max voltage and we have the max current, we may thus deduce that this voltage will be equal to this resistance will be equal to 282.84 volts divided by 6 amperes, so that we finally have the resistance being 47.14 ohms. A different option you could have used the RMS formula for the current, where IRMS is equal to Imax over the square root of 2. Where IRMS is equal to 6 over root 2, which is equal to 4.24 amperes. And we take that and because we have the RMS voltage, we may thus use that to deduce the resistance using V over I, where V is the VMS voltage, given as 200 divided by 4.24, which tells you that the resistance is 47.17 ohms. Okay, so your correct final answer will be any value in the range between 47.14 and 47.17 ohms. There. 9.2.2. Oh, this is 0.1. 9.2.2. 9.2.2 is asking us to calculate the energy consumed by the device in 2 hours. Now, the energy consumed by the device in 2 hours will be given by the amount of work done, okay? And the amount of work done by an electrical component is given by the current squared through the component multiplied by the resistance times the change in time, okay? The RMS current we know is 4.24, which was calculated, okay, multiplied by 47.17, which is the voltage we calculated. And 2 hours is, we count this in seconds, right? So this is 2 hours times 60 minutes times 60 seconds, which is approximately 7,200, and this should give you that the work done is equals to 6.11 times 10 to the power 6 joules. Or option 2, you could use the formula that tells you that the work done is equals to the product of the potential difference with the current and the time where you still continue using your RMS values, where your VRMS is 200, your IRMS is 4.24, and your time is 7,200 seconds, coming from this right there, okay? And it'll give you the same answer of 6.11 times 10 to the power 6 joules. Or you could say that this is option 3. You could say that the work done is given by the potential difference squared multiplied by the change in time over R, which is still your RMS potential difference multiplied by the 2 hours, all over 47.27, which is our resistance, thus 6.11 times 10 to the power 6 joules. And 6.10 times 10 to the power 6 joules is also an acceptable answer. And that is it for question 9. Moving on to question 10. I'm just going to clear that. Question 10, the final question. Ooh, what a beautiful question. A question about one of my favorite sections of physics, the photoelectric effect. Without wasting time, let us get right into it. Okay. Q10. Okay. In a photoelectric investigation, light of different frequencies was radiated on each of the two metals A and B. Okay. The graph of maximum kinetic energy of the ejected electrons from metal A and the frequency of the incident photons is shown. Okay, so we have the maximum kinetic energy of the ejected electrons versus the frequency of the incident photons. Okay, point X on the graph represents an unknown maximum kinetic energy. Write down the numerical value of the gradient of the graph. Okay, in order, the gradient of the graph. So already from everything that you know, or from lessons that you've done in class, you know that the gradient of a frequency kinetic energy, or a kinetic energy versus frequency graph for the photoelectric effect, is given by our constant 6.63 times 10 to the minus 34. Okay. 10.2. Define the term work function. Okay. The work function is the minimum energy required to eject an electron from a metal surface. Okay, with your keywords being minimum energy required to eject an electron. That is your key phrase. Okay, this is 10.2.1. 10.2.2. Calculate the work function of metal A. Okay, we know that the work function is given by the Planck constant multiplied by the frequency. Okay, and that will be 6.63 times 10 to the minus 34 into 5 times 10 to the power 14. Okay. Now, this 5 times 10 to the power 14 is the initial frequency, is the frequency that we first recorded when the kinetic energy is 0, okay? It's this frequency right here. And it is given at 10 to the power 14 hertz, which is why it's 10 to the power 14 hertz. That's the work function will then be 3.32 times 10 to the minus 19 joules. Okay, and 10.32. We are required to show to calculate the value of x shown on the diagram. For this, we may use the gradient formula. The gradient formula tells us that the gradient is equal to the change in kinetic energy divided by the change in frequency. Okay, now we have already written that our gradient is the Planck constant, 6.63 times 10 to the minus 34, which is equal to our change in energy. Our change in energy will be x minus 0, and our change in frequency will be 12.54 minus 5. All of this is to the power, let me just write it all out. This will be 12.54 times 10 to the power minus 14 minus 5 times 10 to the power minus 14. Thus, x will be equal to 5 times 10 to the power minus 19 joules. Okay. Another option you could have used is the option, okay, let me just write that here for option 2. You could have used the formula that tells you that the total energy is equal to the work function plus the total kinetic energy. Okay, and we know that the energy is given by HF, the work function is given by HF naught, and the kinetic energy is given by 1. Let's just leave the kinetic energy as is. Let's leave the kinetic energy as is, okay? Because remember that x is an unknown maximum kinetic energy, okay? X is an unknown maximum kinetic energy, which is why we are going through all of this. Now, we know that our h, this side is 6.63 times 10 to the power minus 34. Our frequency is 12.54 times 10 to the power 14, because remember that is where the maximum kinetic energy occurs. The maximum kinetic energy occurs when the frequency is 12.54 times 10 to the power 14 hertz, okay, which is equal to our Planck constant again into 5 times 10 to the power 14 plus EK max. Now, EK max is equal to x. This tells you that x is equal to 5 times 10 to the minus 19 joules. Okay. Moving on. 10.4. How will each of the following be affected if light of frequency 12? Okay, let me just write this as 12.4.1. How will each of the following be affected if light of frequency 12.54 times 10 to the power 14 hertz, but of higher intensity is used? Okay, now the value of x will not change, because remember that the value of x is the maximum kinetic energy, and the maximum kinetic energy is dependent only on the temperature and not on the intensity of the light. It's only dependent on the frequency, okay? when I say temperature, you must think frequency. It's only dependent on the frequency. So the value of X will stay the same. It will have no effect. (10.4.2). Now, the number, does it increase, decrease, or have no effect on the number of photoelectrons emitted per unit time? Now, if the intensity of the light has increased, it means that the number of electrons, the number of photons that are incident on the surface therefore increases. So if the number of photons that are incident on the surface increases, then it then tells you that the number of photoelectrons emitted per unit time also increases. So this will be increases. And finally, 10.5, the big one, the big shebang to close it off. Okay, we are asked to redraw. The graph above, okay, and label this graph as A. On the same set of X's, sketch the graph for metal B. Label the graph as of B, because B has a higher metal function, okay? So this will be EK max, and this will be frequency in hertz, okay? So if metal A has that kind of graph, then metal B will have that kind of graph, because metal B has a higher work function. And remember that the higher the work function, then the higher the maximum kinetic energy. Or they might have the same maximum kinetic energy, just on different values of the frequency, depending on how you see it. But yeah, that is the end of our question paper. I hope you enjoyed having physics, the June 2023 physical sciences paper 1 exam with me, and I will see you next time.